Welcome to my PhD defense. My name is Raphael Sulzer, and in the coming 45 minutes I will present the work that I conducted as a PhD student during the past 3 years. During this time I was mainly in the LaSTIG lab at IGN, where I was supervised by Loïc Landrieux and Bruno Vallée. And I was also supervised by Renaud Mallet from the Imagine lab at École de Pont. And now I want to start this presentation by quickly explaining the title of my PhD, which is Learning Surface Reconstruction from Point Clouds in the Wild. Let's assume we have a real object and we want to create a digital copy of it. And we are mainly interested in the surface of the object, so not its material, weight, or appearance, but just the surface. And the question is, how can we create a digital copy of a real surface? And one answer can be to scan the object, such as I've shown here. So on the left we can see a simulation of a range scanner which can measure the distance from the sensor, shown with the orange dot, to the object. And this scanner, but also other scanning technologies, allow us to create a 3D point cloud of the object, here shown on the right. And now, given this point cloud, we can approximate a continuous surface from the discrete point measurements. And this step is what we call surface reconstruction from point clouds. And we do this, of course, to visualize the object. Usually a closed surface provides much better visualization than just the discrete point samples. And this also allows us to, for example, texture the surface, so we can apply any texture or color we want to change the appearance of the surface. But more importantly, we can also analyze the surface and use it for numerical simulations instead of doing costly or time-consuming real-world experiments. So for example, if we have the surface of a whole city, we can use it for wind simulation, such as I've shown here on the bottom right. But there are many other applications as well. And now going back to this bunny object, if we take a closer look, we can see that we missed some areas when scanning it. And where we miss points, our reconstructed surface is not very truthful. So for example, we can see here that the bunny ears are not separated well. So the problem of surface reconstruction is that we do not know what lies between the measured points. And traditionally, this problem has been solved by using different kinds of handcrafted priors during the surface reconstruction process. But the question that came up a couple of years ago in computer vision and deep learning is, can we learn it? So can we learn how the surface looks like between the measured points? And I can give you the answer right away, which is yes, we can. So for example, we can design a supervised learning algorithm that is trained on pairs of point clouds and true surfaces. And this algorithm is then able to reconstruct a truthful surface even from defective input point clouds. So here in this case, the bunny ears on the bottom right are separated much better because we have shown this network many examples of how bunnies look like. And right around when I started my PhD, first approaches came up that started doing this. And this works quite well with small objects, but in my PhD I wanted to go one step further and ask, can we reconstruct the surface from a point cloud like this one here, for example? So this is what we call a point cloud in the wild, meaning it was acquired outside of the lab in an uncontrolled environment. And this can result in a point cloud that has missing data, outliers, noise, and that samples the surface non-uniformly. It can also be of large scale, up to millions of points and more, and it can come from multiple modalities such as LiDAR or multi-view stereo, like the one shown here. And lastly, we usually do not have access to true surfaces from point clouds in the wild, which means we do not have training data, such as we might have for small, well-known objects. So the question is, how can we build a supervised learning algorithm that, given a point cloud in the wild, can reconstruct a truthful surface? And this is the question I'm going to answer in this presentation. So in the first part, we are going to look at the input of a learning-based surface reconstruction algorithm. In the second part, we are going to benchmark state-of-the-art surface reconstruction architectures and discuss their benefits and shortcomings. In the third part, I will discuss how we can incorporate visibility information into the learning process, which improves the generalization capability of learning-based reconstruction. And finally, in part 4, I'm going to show how we implemented a learning-based architecture that can scale to process point clouds with millions of points. So in this first part, we are going to look at how we can create synthetic point clouds that have similar characteristics to point clouds in the wild, but are sampled from known surfaces. And the first question that comes up here is, why can we not train on real point clouds and corresponding true surfaces? So if we would have a ground truth surface and defective LiDAR or MVS point clouds of this surface, this would be the perfect training data set for our learning algorithm. But the problem is generating such ground truth surfaces requires a lot of data. So even for this one object here, we need a lot of viewpoints to densely cover the surface. And this, of course, does not scale to hundreds or thousands of shapes that are required for most learning algorithms. So we simply do not have enough ground truth surfaces from real objects. But what we do have is a lot of object surfaces from shape collections, such as ShapeNet. And what we do in our work is we synthetically scan these objects. And like this, we can simulate range scanning point clouds, but also point clouds from multi-view stereo. And for synthetic range scanning, we use existing work from Berger et al. And for simulating MVS point clouds, we implemented a process where we place synthetic sensors on multiple bounding spheres around an object and shoot rays at the object. And the intersections of the ground truth mesh and the shot rays build up the point cloud. And we also add Gaussian noise and outliers in the form of uniform samples drawn from the bounding box of the object. And you can see here that the two different scanning simulations, the range scanning and the MVS scanning, they create point clouds with different characteristics. But more importantly, they can create point clouds which resemble those of real point clouds. So here in this case, we have a nice ground truth surface of a real object which was made from the very densely sampled LiDAR scan that I showed before. And this allows us to compare synthetic and real scans of this object. So synthetic scans on the bottom, middle and right, and real scans on the top, middle and right. And what this shows is that such synthetic scanning is much more realistic than simply directly sampling the surface like we see on the bottom left. Because such a uniform sampling completely ignores these typical occlusions that we have when we scan a complex object. Unfortunately, many learning-based surface reconstruction algorithms have so far only been tested on such uniformly sampled point clouds, like the one on the bottom left. So to summarize this, we create synthetically scanned point clouds with real characteristics to train and evaluate learning-based surface reconstruction algorithms. And we provide scanned versions of the 4 different datasets I listed here. And the specialty of these datasets is that we provide the point clouds with the sensor position for each point, which we will later see can be very useful. So here we can see some examples of these datasets. We have relatively simple shapes in the top row from ModelNet, slightly more complex shapes from ShapeNet, and then the small dataset from Baga et al., which we use for testing. And links to these datasets are available on the GitHub repository DSR benchmark, which stands for Deep Surface Reconstruction Benchmark. And I will now quickly present some of the results of this benchmark. So in this part, we will look at how well some of the recent learning methods compare to more traditional surface reconstruction methods. In the end, the goal is of course to reconstruct surfaces from real point clouds in the wild, but to have a measurable proxy of the reconstruction quality of different methods, we test them on the datasets that I have just introduced, which have the characteristics of real point clouds, but also a ground truth surface with which we can train learning algorithms and measure their reconstruction quality. And for this, we conduct 3 different experiments. In the first experiment, we reconstruct surfaces from known sampling defects and known shape categories. We use ShapeNet for that, which has 13 different shape categories, of which this airplane class here is one example. And we generate point clouds with 3000 points per shape with the synthetic scanning, and we add Gaussian noise to the point clouds. In the second experiment, we reconstruct surfaces again from known shape categories, but this time from unknown sampling defects. So we keep the same trained models as before, but we test on point clouds with 10,000 points and 10% added outliers. And in the third experiment, we reconstruct surfaces from unknown shape categories, but with known sampling defects. And we do these experiments with free learning and 2 traditional surface reconstruction methods. And what is important to mention is that we assume we are in a supervised learning setting, so we have a training and a validation set. And with these datasets, we can also tune the parameters of the traditional surface reconstruction methods to make this a fair comparison. So we test 5 methods on these 3 different tasks. 2 traditional methods which are already quite old, but we will see throughout this presentation that they can still outperform learning-based reconstructions in some tasks. Then we test 3 learning-based methods, and I will later introduce 2 of them in a bit more detail when we talk about scalability, but for now we will mostly look at how the methods perform on object-level reconstruction and how well the methods generalize to unseen data. So in this first experiment, where we reconstruct surfaces from known sampling defects and known shape categories, we can see that the learning-based method performs much better than the traditional method for this task. So the learning method has learned the sampling defects here and can thus reconstruct a more accurate surface. The surface of the screened Poisson algorithm, so SPSR, is not as smooth and also fragmented with a lot of small components, which is shown in this small inlet in orange. And for a quantitative evaluation, we measure the volumetric intersection over union between ground truth and reconstructed surface and the number of components of the reconstructed surface. And this last one is a metric that is usually not measured in benchmarks, although it is also quite important. So we only deal with single objects in this benchmark, so they all should have only one component. But some methods reconstruct multiple components, which of course is not practical if we want to further process the surface. But the takeaway message here is that in this in-distribution setting, learning-based methods can provide more accurate reconstructions compared to traditional methods. Now for this next experiment, we keep the same trained models, but we test them on point clouds with a higher density and with 10% added outliers. And as you can see, the traditional screen Poisson surface reconstruction can deal much better with this domain shift. So also for this method, we did not change any of the parameters, and the learning-based method does not reconstruct a usable surface here, even though it has seen airplanes before, but not from such point clouds. And in fact, most learning-based methods struggle with this setting, and the traditional methods perform better. Although again, you can see a sort of trade-off between the number of components and the volumetric intersection over union, which is quite typical for many reconstruction algorithms. And now for this last experiment, we train the networks on the smaller and simpler ModelNet dataset. And we test again on ShapeNet with the same sampling. So the difference to the previous experiment is that the networks have never seen an airplane before, but are asked to reconstruct it. And again, for this task, the learning-based networks do not work so well. So maybe here this learning architecture tries to reconstruct a table or something like that, which was in the training set. And indeed, again, most networks struggle in this setting because they overfit to the smaller and simpler ModelNet dataset. And the traditional methods do, of course, not have a problem with this domain shift and again reconstruct more accurate surfaces. So to summarize this, learning-based surface reconstruction outperforms traditional reconstruction methods when sampling and shape categories are known. But the tested learning methods do not work well for unknown sampling defects. And they need a large training set with complex shapes. And we now address these two issues in 2 and 3 in the next 2 parts. So in this part, I will show how we can incorporate visibility information into the learning process, which greatly improves the generalization capability of learning-based reconstruction. And this work has been published at ICPR this year. So I have shown this a couple of times for the simulated scans, but in general, almost all 3D scanning techniques allow to recover the sensor position during acquisition. And then this sensor position can be used to relate each observed point with a line of sight. So this line of sight is a segment between a point and its sensor. And up to uncertainties in the acquisition, this segment must lie outside the scanned surface, because in fact it is the path of reflected light from the surface point to the sensor. And we call this additional information visibility information. So now the idea is to use this information in the reconstruction process. And we do this by augmenting a point cloud in 2 ways. First, we add these line of sight vectors here in dark blue to each observed point. So these vectors are directed towards the corresponding sensor of the point. And this can help the network to find the correct orientation of the surface. And second, we place before and after points along the extended line of sight. Before points in yellow here and after points in pink. So these points are placed right in front and right behind each observed point, and these points can mainly help to identify empty and full spaces within the reconstruction domain. And as shown here, for example, they can help to better identify such cavities. And we simply feed these before and after points as additional points to the network. And to identify the type of point, so either a before point, an after point, or an observed point, we simply also add a point type identifier, which is a 2D one-hot encoded vector that is unique for each of the three types. And we also add this to the network input. So now if we apply this to a point cloud, we can see that the new point cloud looks like this, as shown here on the right. And to feed such a visibility augmented point cloud to a surface reconstruction network, we only have to apply 2 small modifications to the network. And these modifications are very general and can basically be applied to almost any network. So first we increase the number of channels of the first layer, which is usually from a point cloud encoder. So we increase it by 5, 3 channels for the sightline vector coordinates, and 2 channels for the point type identifier. And second, we only have to adjust the batch size during training to accommodate the 3 times larger point cloud. So 3 times larger because for each observed point, we have 1 after and 1 before point. So now we trained a couple of surface reconstruction networks on the ModelNet dataset, on the simple ModelNet dataset that I've shown before. So one time with and one time without these modifications, and we input bare or visibility augmented point clouds accordingly. So here you can see a result of convolutional occupancy networks. And what you can see is that this cavity below the tabletop is only well reconstructed when using the augmented point cloud. Here in this case, we do have a slightly worse reconstruction on the bottom left, where this fin structure is actually better reconstructed from the bare point cloud. So for fin structures, the after points are difficult to place. I show it on the top right because even right behind an observed point, we can already be in empty space again. So here, this is a sort of small failure case. But in general, the method even works better on fin structures, even though the inside points might sometimes provide slightly wrong information. But where we can see the most improvements is really for this type of concavities. So now for this first result, we trained on ModelNet and test on ModelNet. And in this in-distribution setting, we can gain between 1 and 4 points in mean intersection over union, depending on the method. But where we can see an even bigger improvement is when we reconstruct shapes from out of distribution point clouds. So for reconstructions from unknown sampling and from unknown object categories. So for the following results, we use the same models which were trained on the simple ModelNet shapes, here with 3000 points per shape. And then we reconstruct real-world point clouds with these trained networks. So this is an MVS point clouds from the Middlebury dataset. It has around 10,000 points and is quite a bit noisier than the training point clouds. You can see that best on the input point cloud on the top left, where you can see these off-surface points here. And here we can see a much better, so more accurate and more compact reconstruction for all methods when using the augmented point cloud. This is the so-called scan1 from the DTU dataset, and it is sort of an open scene of a bucket. So this bucket is only scanned half, And again, we only trained the networks on closed objects. And we can see that the models which are trained without visibility information struggle to generalize to this different setting, while the models which are trained with visibility information generalize really well. This is a LiDAR scan from tanks and temples. Here we subsample the LiDAR scan to have around 10,000 points. Again, the training point clouds all have 3,000 points only. And here the reconstructions from the augmented point clouds are more detailed and again more compact. And here I visualize a cut of this statue, and you can see that the reconstructions from the bare point clouds are actually hollow. So here you can see it here and these parts here. And this is because the network cannot well distinguish between inside and outside. So this is probably due to the fact that the networks learned some sort of dataset bias from the ModelNet dataset. And for most methods, we do not have this problem at all with the augmented point clouds, which reconstruct a nice closed surface of this statue. And lastly, here I show a reconstruction of Poco, which can also scale to smaller scenes. And again, the network has only been trained on the closed ModelNet objects. And with augmented point clouds, the reconstruction is much better. So this time it is the reconstruction on the right, which has been done with the augmented point clouds, versus the reconstruction in the middle, which has been done with the bare point clouds. So here you can see some quantitative results for the out of distribution setting. So here we evaluated reconstructions on ShapeNet from the models trained on the simpler ModelNet shapes. And we see very big improvements for some methods, up to 44 points in mean intersection over union. And on the right, I show mean runtimes of the methods for reconstructing one object. And I'm going to come back to the absolute values later, but what is important to note here is that the runtimes of the networks almost do not change when we use the visibility augmented point clouds. So here you can see part of an ablation study we did. And this again shows that adding both augmentations, so sightline vectors and auxiliary points, is beneficial. And what is interesting to see is that adding the two augmentations combined produces even better results than adding the ground truth normals. While of course having true normals is a very challenging problem in itself. And in the paper we did additional ablation studies. If you're interested, you can have a look in the paper. So now to summarize this part, visibility information can be added to most surface reconstruction networks with very little modification and little to no added runtime. And visibility consistently improves the reconstruction quality as well as the robustness of surface reconstruction networks to domain shifts. So the bottom line here is do not throw away your sensor positions. Our code and data is available on the GitHub repository DSRV data, which stands for Deep Surface Reconstruction with Visibility. Now, in this last part, we're going to answer the question how we can make learning-based surface reconstruction scale to large scenes with millions of points and present our proposed solution for this. And this work has been published at SGP in 2021. Now, before we discuss our architecture, I want to quickly explain how most of the algorithms that we have seen so far roughly work, and why they are usually not suited for large-scale point clouds, or to process large-scale point clouds. So the idea of some of the first learning-based methods that could reconstruct a non-intersecting and closed surface was to represent the surface as the decision boundary of a neural network. So the methods have an encoder that encodes the point clouds, and then in these first works there was usually a fully connected network that was trained to classify query points as lying inside or outside the sought surface. And then the surface is defined as the decision boundary of the network. And to extract an explicit surface, one can use an isocontouring algorithm such as margin cubes. And here I show an example of an architecture that works like this. So here the whole point cloud is encoded in a low-dimensional vector. And the network is then trained to classify the correct occupancy for a query point. Now the problem with this is that encoding the entire point cloud does not scale to large point clouds. And this is for two reasons. First, it is simply too computationally expensive, especially if the point cloud has up to millions of points. And second, it is simply not possible to encode an entire scene, for example, in a low-dimensional shapecode. And as a result, these networks usually specialize to shape categories which are seen during training. So I remind you of the experiment that I showed in the beginning, where we trained on the simple ModelNet shapes and tested on ShapeNet. And we saw that even more complex architectures than the one that I've just shown still overfit to the training shapes. A newer idea is to encode each input point separately together with its local neighborhood, and then interpolate query point features in latent space, and decode these features to get an occupancy for the query point again. And the benefit of this is if we look at a surface part included in one of these local neighborhoods, we can sort of hope that the surface part is also present in other objects. The problem here is that for decoding, we now need to do a nearest neighbor search and an interpolation. And we also have no global view anymore. So if we look at the pros and cons of local and global approaches, we can see that a global approach allows for learning shape semantics. So here, for example, because the network sees the whole bunny, it can sort of reason from that. But it can be very memory expensive, a global approach, especially if the point cloud gets large. Local approaches, on the other hand, allow for a better memory and compute control and for better generalization, because we have sort of this shared learning of parts from different shape categories. But that comes with the downside of no global view, and thus local approaches do generally not allow to learn shape semantics. But this better memory and compute control and better generalization capability is very important for reconstructing surfaces from point clouds in the wild. where we can have very large point clouds and where we do not necessarily have training data for the object categories we want to reconstruct. So now what would be great is if we could have a combination of both local and global receptive fields to share their benefits. And this is what is done in points to surf. So this approach encodes a local neighborhood of the query point and a global subsample of the whole point cloud, which mainly helps to distinguish inside and outside space. But again, depending on the size of the global subsample, encoding it can be slow. And the local neighborhood still has to be computed for each query point. Another idea is to aggregate local point features in grid cells, and then use a convolutional neural network to process these features and then interpolate query point features from grid nodes, and again decode them to get the occupancy of the query point. The problem here is the choice of the input grid size. Taking a dense grid will simply not scale to large scenes, so remember this is actually in 3D. And taking a coarse grid may aggregate too many points in one cell and thus lead to a loss of information. So this makes it hard to efficiently train on point clouds with different densities. So now what we propose in our work is to triangulate the point cloud using a 3D Delaunay triangulation, then encode local neighborhoods in the form of subgraphs of the triangulation, and then classify cells of the triangulation to lie inside or outside the surface. And then we can directly extract the surface as the interface between inside and outside cells of the triangulation, and do not need to run margin cubes, for example. But of course, also our architecture is not free of any problems. So here we have an interpolating approach, which means the surface interpolates the point set. So if we have a lot of noise, for example, in the point cloud, the extracted surface may also be noisy. So now the idea of using a Delaunay triangulation for surface reconstruction is of course not new. And there is a very popular method that is often used, especially for large-scale surface reconstruction. And this method uses explicit visibility modeling and a graph cut to classify cells to lie inside or outside a surface. And I list here some of the works that developed and improved this method, and I'm now going to explain how one of these approaches roughly works and show some of its shortcomings and present our proposed improvements on top of it. So the method starts with an input point cloud, and as I've shown before, for most acquisitions we also know the position of the sensor that recorded the points. And the point cloud is then triangulated with a 3D Delaunay triangulation. And the cells that lie between a sensor and a point have evidence now to be empty, because they're crossed by this line of sight. And all cells that lie directly behind the point are usually full. But now zooming in on a real point cloud, we can see that acquisitions in the wild are often contaminated with noise. And noise and also outliers can not only lead to imprecisions in the point cloud, but also to defective visibility information. And this in turn leads to the problem that the empty full labeling is sometimes ambiguous. So here on the left cell with a question mark, this cell here, we have evidence for an empty and a full classification. So this is evidence for an empty and this is evidence for a full classification. And on this cell here, our input point cloud and visibility information is simply not dense enough to identify empty or full space. So we have no evidence for empty or full classification here. And the common approach to solve this problem is to find an empty full labeling by minimizing an energy such as the one that I've shown here, which was introduced by Labattu et al. And this energy can be efficiently minimized using a graph cut. So for conflicting areas or for tetrahedra without any visibility information, labels are propagated based on a prior that favors smooth surfaces. Now, this method is very popular and it leads to impressive visual results for large-scale point clouds, but it does not always make the best decision locally. And to improve these local empty or full decisions of the graph cut, we use a graph neural network to calculate empty full likelihoods in our proposed approach, instead of using handcrafted functions or rules. So the graph neural network computes an empty full likelihood for each cell from the geometry and visibility information in the local neighborhood of this cell. And we then input these likelihoods again into the same energy for global regularization. And I will show in a minute that using the likelihoods from the trained graph neural networks can locally often lead to more accurate empty full predictions and thus to a more accurate surface. So how do we compute these likelihoods? First, we initialize all tetrahedra in a small subgraph with visibility and geometric features. And I'm not going to go into detail about the features, but what is important to mention is that the features are all inherently rotation and translation invariant. And we only standardize the features per object to have zero mean and unit variance. And then we apply a graph convolution scheme, which I'm also not going to explain in detail, but what happens basically is that we aggregate the feature information around the cell's wandering neighborhood. And we iteratively apply this process until we reach the target cell. And finally, the embedding of the target cell is processed by an MLP, which outputs the empty full predictions, which we then process with a graph cut. So to make a first conclusion, we use what we call a Delaunay-Graph neural network, DGNN. So a graph neural network operating on the dual graph of a Delaunay triangulation. Now the Delaunay triangulation has the benefit of being adaptive to the local point density and providing a data structure that enables a very fast neighborhood search. Then we locally predict empty full likelihoods for each cell of the Delaunay triangulation, which enables a high memory and compute control and good generalization. And finally, we process the empty full likelihoods with a graph cut, which provides additional robustness. And now to train and test our method, we use point clouds with a variety of different characteristics and defects. And we generate these point clouds with the synthetic scanning procedure that I introduced in the beginning. And for this first test, we generate point clouds with 5 different scanner settings for making point clouds with low resolution, with a high resolution, and with noise and outliers combined. And now we applied our method and also other learning and non-learning based methods to reconstruct a closed surface from these scans. And here we can see the reconstruction of a low resolution scan. So our reconstruction is on the right. And we compare again to convolutional occupancy networks, which in this case, does not generalize from the ShapeNet training objects to this unknown object here. And we also compared to the screen Poisson algorithm and to the method of Labatut et al., which I explained before. And here we can see some defects for each reconstruction. Quantitatively, our reconstruction is still the best. Here we show the reconstruction of a high-resolution scan. This is an easy problem for which most methods produce a high-quality surface. Still, we can see some defects in some of the reconstructions. And again, our method produces the best result. And finally, a very difficult scan, which includes a high level of noise and outliers. We can see that even our reconstruction is quite noisy, but still produces a slightly smoother and more accurate result than the other tested methods. And we chose to train and evaluate our method on such difficult problems because we want to see now how the method performs when reconstructing a surface from real-world MVS point clouds that are often quite noisy. And for this and the following reconstructions, again, we used the same model trained on ShapeNet with the synthetically scanned point clouds I showed before. So here I show a result of an MVS point clouds from the ETH3D dataset. This whole scene has more than 1 million points. And because the learning part of our method works purely local, we can scale it to such a big scene. And if we zoom in, we can see again that this is a difficult problem even for our algorithm. But when we compare the reconstruction result to a method which, similar to Labatut et al., uses handcrafted rules and functions for computing the empty full likelihoods, we can see that our learned likelihoods produce a much better result. So here the staircase as well as the texture on the wall here are better reconstructed. So here we can see that the wall has this fine-grained texture, which is reconstructed in our case, but not here. Here we show another scene from ETH3D, which has around 2.5 million points together with our reconstructed surface. Again, we zoom in, and here we compare to the screen Poisson reconstruction again and another energy-based method, which are still one of the few surface reconstruction methods which can scale to large scenes like this. And again, our algorithm produces a more accurate and more complete reconstruction at the same time. And here we compare again to convolutional occupancy networks, which has a sliding window mode to scale to larger scenes. But again, as we've seen before, it doesn't generalize well to unseen objects. Now, we developed DGNN in 2020, sort of a lifetime ago for deep learning architectures, but now we tested it again on the benchmark that I presented in the beginning. And for the first experiment, which is the in-distribution setting, we can see that the two newer learning-based methods, shape as points and POCO, generate reconstructions with a higher IU. However, our reconstructions are slightly more compact on average, so they have less fragmented surfaces, as you can see by the number of components on the right. In the second experiment of the benchmark, where we train only on low-resolution point clouds and test on high-resolution point clouds with outliers, we can see that also DGNN overfits to the sampling characteristics of the training set. However, what I have just shown is that we can train DGNN on point clouds with different characteristics and different defects on this at the same time, and then avoid this overfitting. While, for example, convolutional occupancy networks then still had the problem of overfitting to the shape categories. Now for these third experiments where we trained on known sampling defects and tested on unknown shape categories, we saw that other learning-based methods greatly improved with added visibility information. So to make this a fair comparison, I show the results of the other methods with the added visibility information. So this is with the modifications I introduced in the third part of the presentation. And then these methods perform almost on par with DGNN. However, DGNN still produces a more compact surface. And now we can take a look again at the runtimes of the different methods. So here are, on the left, are runtimes for reconstructing an object from 3000 points. And we can see that DGNN is the second fastest learning method behind shape as points, so SAP. But in contrast to shape as points, our method can natively scale to scenes. So for shape as points, this would probably have to be done with a sliding window approach. Such a sliding window approach does exist for convolutional occupancy networks. And we measured it on the right, and here our method still is around 2.5 times faster on a scene. So here we measured the reconstruction time of a scene with 500,000 points. Now lastly, we did an ablation study where we trained on ModelNet and tested on ModelNet and ShapeNet. Again, if you're interested in the full study, you can have a look in the paper. But I just wanted to mention two things here. The first is that we see with DGNN the same that I have said many times. Visibility information helps the network a lot, and even more so in the out-of-distribution setting here on ShapeNet. Nonetheless, I think it is very interesting to see that the network can still reconstruct surfaces with a high IOU even without these visibility features. And in this case, that means only based on geometric features per tetrahedron, such as the volume of a tetrahedron, and its longest and shortest edge, and so on. And the second interesting thing is that we can also directly use the network predictions without the subsequent graph cut. And when we are in the in-distribution setting, this results in an even better reconstructed surface, slightly better. And indeed, the graph cut is mainly needed for out-of-distribution reconstruction and real-world scans, which are very noisy and have outliers very often. So to conclude this, DGNN combines an efficient and adaptive data structure, which is the 3D Delaunay triangulation, with a powerful class of learning algorithms, which are graph neural networks. And this in turn allows us to scale learning-based surface reconstruction to process real-world point clouds with millions of points. Again, our code and data is available on the GitHub repository DGNN. And lastly, I want to mention another repository which I have developed during my PhD, which is called Mesh Tools. The repository includes a couple of small tools for mesh processing, such as the synthetic scanning I introduced in the first part, but also, for example, the implementation of Labattu et al., which is used for comparison a lot during my PhD, and which is still a very good non-learning based surface reconstruction algorithm. And the code is written in C++, so it's fast and it makes heavy use of Seagull and OpenMVS. So to conclude this presentation and my PhD in one slide, I have presented a benchmark for learning-based and traditional surface reconstruction algorithms. I have introduced a method to incorporate visibility information into the learning-based surface reconstruction algorithm. And I have introduced a method for large-scale learning-based surface reconstruction. And all the datasets and the code that I have developed are available online. And now I want to thank you for your attention, and if you have any questions, feel free to contact me.